Thank you. So yeah, thanks for the introduction. My name is Johan. I'm a researcher at Microsoft Research, and I'm going to tell you about an exascale archival storage system that we've designed and prototyped over the past 8 years inside Microsoft Research that's currently under development for productization. So before I dive into the technical content, I want to just take a moment to just set the scene a little bit. I think some of the remarks in the opening session actually about the kind of the honeycomb analogy I think really resonated with me, because I think the entire project has really been, first it's been a very long ongoing partnership. We've been going at it already 8 years. This is a partnership between Azure Storage, Microsoft Research, and especially now, other parts of the company. And in designing and prototyping the system, we've really had to innovate across all of these areas that you see here, right? From basic research in physics, material processing, microscopy, machine learning, robotics, industrial design, you name it. And we really built Silica from the ground up and cross-optimized everything from the materials up to the cloud service layer, primarily to be a cloud service that serves archival workloads. So, each of these boxes could be several talks on their own. For this talk, I'm going to focus particularly on these things, but I'm going to touch a little bit on all of them to kind of give you a sense for how everything comes together. There's a lot of stuff I'm going to have to skip. Come talk to me, particularly about error correction and erasure coding. So, come talk to me. We also had a paper at SOSP, the Top Systems Conference last year, and we have an extended version of that paper coming out in Transactions on Storage soon. So you'll be able to get more details from that later. So, what do I mean by archive? Turns out there's actually several different kinds of archive. When people think about archive, traditionally, I think the kind of mental model people had for archive was business continuity, disaster recovery, which is you see here as listed as backup. This was effectively what magnetic tape was originally servicing. But it turns out it's actually quite a small fraction of the entire market, particularly the available market today. There's also active archive, which some of you I'm sure are familiar with. This is providing large amounts of low-cost storage for workflows that have analysis in the loop. So this is the kind of stuff that scientific computing and scientific measurements use, like at US National Labs. I see Gary over there. CERN, RECAN, UK Met Office. And for this vertical, better latency will increase usage, but it'll also unlock new applications because you're able to now, do analysis with more data in the loop. Then you have long-term archive, which is a significantly growing business today. So here, you have scientific measurements, personal data, regulatory data, stuff that has to be kept around for regulatory and contractual reasons. And in this segment, offering lower dollar per terabyte cost will actually make the sector grow quite significantly. And the last one I want to mention is actually an interesting one, is what we call preservation, which is quite a nascent business, and it's slightly different than long-term archive in that customers here actually really, really care about the media properties. So they're extremely paranoid about things that could go wrong. Think the media and entertainment industry, and many other in this digital economy that we have. There are many companies whose sole business model is just generating IP that takes a lot of time, effort, and money to come up with if it's lost. And so these companies really want hundreds of years durability guarantees. They want true air gap. So they want the ability that once the data is written, it's not going to be interfered with. It's not going to be overwritten or disturbed even by malicious or accidental intent. And they want it to even withstand benign neglect. So effectively, you can leave the data there and come back in 100 years, and the data is completely safe. And so with Silica, we looked at building a technology that can kind of address this entire spectrum of archive. But why do we start doing this? Well, it turns out that despite the fact that you have this, this really big need for archival storage, we still do not have a storage technology that can offer sustainable and cost-effective long-term archival storage. The most cost-effective alternatives today are magnetic, hard disk drives, and particularly magnetic tape, which offers the lowest dollar per terabyte cost. And these underpin most archival storage in the cloud today. Of course, the problem is that magnetic media degrades and is susceptible to interference over time. And so there's two main consequences of this. One is we need to refresh the data. So every few years, we need to migrate the data to a new generation of media. So for long-lived data, we have to pay a periodic cost, both financial and a kind of a system cost of provisioning bandwidth to refresh, to keep this data around. And in the interim between these migrations, we need to expend energy to scrub the media. So read the data back, do any sort of fixity checks, use erasure coding to fix up the data and maintain the same level of durability. And so this is not great. And of course, the consequence of all of this is that with magnetic media, the cost in terms of emissions, energy, and dollar cost scales with the lifetime of the stored data, which is not great when you're trying to store data for decades or hundreds of years. And so we think glass offers a truly disruptive media for archival storage. And why is that? Well, glass is a very low-cost material. It's fused silica. It's an incredibly durable media, so it's chemically inert. It has virtually unlimited lifetime in the face of many environmental conditions. You can heat it up to the melting point of the glass. You can drop it in water, boiling water. You can, it withstand surface level scratches. You can microwave it, and it's totally fine. It's not susceptible to electromagnetic fields, so things like EMPs and solar flares. And it gives us a worm media, and which is actually impossible to overwrite even by accident or under malicious intent. And I'm going to talk a bit about those properties later in the talk. So it doesn't suffer from bit or media rot. The way we store information is by making permanent modifications inside the glass material, which means that we don't need any sort of scrubbing. So once we write it, we can leave the data in place forever. And so by switching to this media, we believe that archival storage systems built underpinned by this media can achieve what we call operational proportionality. That is, the cost in terms of emissions, energy, and dollar can now scale with the operations that you perform on the data rather than the lifetime of the data, which is really how it should be for long-lived data. So for the rest of the talk, I'm going to tell you kind of how do you build such a system and show you some evaluation to give you a sense for how the service will operate. So to write data in glass, we use technology called femtosecond pulse lasers. So people typically think of lasers, they think of continuous wave lasers, so continuous laser beam that you see in a light show. Femtosecond lasers are very different. They fire incredibly short pulses on the order of 10 to the minus 15 seconds. So you get an incredibly short pulse, but very high peak power. And then you focus that pulse inside the bulk of the glass media. So I have a piece of glass here. You can come around and see it later. And what happens is at the point of focus inside the media, you get a permanent modification called a voxel. And here at the top, you can see an SEM image of 4 of these voxels at the top. So I'm not going to dive into the physics of this too much, but to give you an intuition for how information is actually stored, by changing the polarization of the laser pulse when we write, we can control the orientation of this voxel inside the glass. And you can see that the different voxels have effectively encode different symbols because they have different orientations in the glass. And so at read time, depending on the orientation of this voxel, the polarization that you read, the polarized light that you read with gets modified in a different deterministic way depending on the orientation of this nanostructure. So this is how we're able to encode multiple bits inside each voxel. So to write, we write 2D sectors. Each sector has over 100 kilobytes of data in it. On the left, you can see a photo from a sector from our prototype hardware. And we write data in glass platters. I have a platter here. This is slightly smaller than the final production system will have. The ones we'll use are 120 by 120 millimeters across. But we've made a deliberate choice not to spin the media. Because spinning media is quite difficult to stabilize. Those of you who work with hard disk drives will know it can take over 20 seconds once you start a hard disk drive before you can start doing IOs to it. And I'm going to talk later, I'm going to tell you in the talk why that's actually quite important. So instead, we move the light. So to get to the high throughputs that you need for an archival cloud service, we use what's called a polygon scanner to scan the laser beam across the surface of the glass. And so we write these 2D sectors like you see on the left side, and then we stack these sectors in Z. So we fill the entire piece of glass volumetrically, except for a small guard band at the top and at the bottoms to, in case, on the off chance that you get any sort of scratches. And so we fill the entire glass volumetrically with data, and we're able to pack hundreds of layers in Z. And yeah, it's worth mentioning, writing is the most expensive part of the system since it uses femtosecond lasers. But I'm going to touch a bit later on how to minimize the cost of that later. So to read, we use completely different technology. We use polarization microscopy. This uses very low powered illumination, so you can even use LED lighting, which means it's fundamentally impossible to overwrite data, even by accident or even under the most extreme circumstances, even with malicious intent. The reader simply doesn't have it doesn't have enough peak power to cause any sort of structural modification inside the glass. So to read, we read 2D sectors at a time. We focus effectively on the layer that we care about reading. We acquire several images in parallel of that sector, which allows us to measure the changes in the polarization of the light that I mentioned before, which is how information is stored. And then we effectively move down in Z. So here you effectively saw a sequential read. Now, one fundamental advantage of Silica media compared to tape is that Silica is fundamentally a random access media. So unlike tape, which you have to spool, Silica, you simply mount a Silica platter, and then you can quickly seek to the location that you want to read from, do your I/O, and then eject the platter and move on to the next one. Now, to decode, we use machine learning. Surprise. Not because it's the hot thing that everyone's doing, but because we're actually able to get the most accurate analog to digital signal conversion. So we get the 2D images from the readers, and then we have a fully convolutional neural network. Those of you who are familiar with computer vision, this is a variant of a UNet, which we developed in-house. And we get the probability distribution for all of the symbols in the sector at once. And then we take those and we feed it into error correction. So, just because we use machine learning doesn't mean the storage is somehow probabilistic or anything. We simply use this to do the analog to digital signal conversion. And then, the actual decode stack is run as a cloud service, which means that we can benefit from all of the great advancements in ML hardware, which is continuously becoming more energy efficient and more performant every year. So this is, writing, reading, and decode. But how do we actually put the whole system together? So like I mentioned, we're focused completely clean slate design. Our only constraints are we have to move equipment into the data center at rack scale, and then it has to fit within the power budget of the data center. So we have complete design freedom.
But we wanted to go with not just our intuition and heuristics. We wanted to study real systems and understand, what do these workloads actually look like in practice, and how can we design our system to serve those workloads, but also to be kind of future-proof. So to do this, we studied a tape-blacked cloud archival service with 10-hour SLOs. I work for Microsoft. You can probably tell which archival service this is. And we looked at the workload characteristics, and we found some quite surprising things that actually went against the conventional wisdom of what certainly the academic community thought some of these archival workloads look like. In particular, we found that archival workloads really need a lot of flexibility. I don't know why the clicker's not working. Oh, there we go. In particular, archival workloads really need flexibility. So if you look at the entire workload, perhaps unsurprisingly, it's mostly write-dominated. So we have 47 times more megabytes written than read, and 174 more write IOs than read. So this isn't that surprising, but it does mean that ideally the write and the read bandwidths should be provisioned and scaled independently in the system. So if you think about how a tape library works, tape drives have both read and write heads packaged together, right? In a system that looks like this, where you have your write rate vastly dominates over your read rate, it just doesn't, it's wasteful, and it doesn't make sense to couple these things together. The next thing is, if you look at just the read workload, there is a lot of variability in the system. So on this graph, you see the tail over median read throughput. So it's basically the ratio between the median and the peak read throughput across different data centers. And so you can see, even within a single data centers, we have over 7 orders of magnitude mean to tail difference. And across different data centers, you have over 5 orders of magnitude difference in the peak to mean. Which means that we need a very modular and flexible library design that can support variability across different deployments, because the workload does not look the same for every data center. And over time, also, the workload evolves. And so we need the ability to kind of deploy as much hardware as we can to service the workload at hand. Now, the next thing, staying on the topic of reads, the next thing is that most people think of archival as the disaster recovery, the first box I had on the second slide, right? They think that archival means very large, sporadic reads, many terabytes. But actually, if you look at the workload is actually IOPS dominated. So people just want cheap storage. They don't want to worry about packaging things together in very large archive blocks, writing them to tape, and then dealing with unpacking them and all of that. People just want to move their data to archive, pay less for it, and that's it. And so on this graph, you actually see on the left y-axis, you see the percentage of all of the read IOs. And on the right y-axis, you see the fraction of all of the bytes read that those IOs represent across the different file sizes, or on the x-axis. And so we see a very skewed distribution. We see 58% of reads are for files that are less than 4 megabytes, but they only make up 1.2% of all the total bytes read in the system. And conversely, 85% of the bytes read are for files that are larger than 256 megabytes, but they make up less than 2% of all the total read requests. So and this is all across 10 orders of magnitude range in file sizes. So it's an incredibly skewed workload. Now, interestingly, this has a couple of implications. One is the per drive read throughput is actually less important than people think, right? People typically say, well, tape libraries have 360, 400 megabytes a second read throughput. That's how much you need. Well, not really when you're servicing a workload that's mostly IOPS dominated and is dominated by so many small reads. For the small fraction of large files, sharding and having enough parallelism in your system becomes quite important. So, take the throughput of the readers, the SLO that you want to achieve, and then with a sufficient level of parallelism, which you do have in the cloud, you can easily cope with that tail of large files. And the second more important consequence also is that with this workload, minimizing mechanical overheads is really, really important. So this includes everything from media transfer, mounting, and seeking delays, right? And tape libraries really struggle to do this. So if you think about a tape library, you have a single gantry robot in the middle, fetching media. So all of the media fetching is completely sequentialized. And so there's a lot of requests spend most of their time queued in the system. Because the media is disaggregated, they need to wait for the tapes to get taken to a reader. Even once they're there, a tape is fundamentally a spooling media, right? So you can even wait up to a minute, and once a tape is mounted, until you spool to the point that you want to read from, and then yes, you get 400 megabytes a second. But it turns out that for a lot of your IOs, you're not actually going to be doing useful work reading for a significant fraction of time, right? And so with a tape library, the good put that you actually get from the system with a workload like this is quite bad. And the last thing I want to do mention on kind of workload characterization is the ingress rate. So if we look overall, if we switch back to writes for a second, and we look at the ingress rate coming into the system, it's actually quite bursty, right? So we have a 15x peak to mean ratio in the incoming write workload. And in Silica, the cost is mostly dominated by the writing, right? So we use femtosecond lasers. They're still a relatively niche technology. They're used for eye surgery. They're used to cut your the glass on your phone screens. They're used in certain applications, but they're not widely commoditized yet, right? Once Silica deploys, that will drive commoditization. But for now, especially at the beginning of the lifetime of the system, it's important that we ensure we maximize write drive utilization. So we do what people typically do in the cloud. We leverage the massive scale, and we aggregate. So it turns out if you do something as simple as just buffering your data in an upper tier, let's say a hard disk drive tier, for several days, you can see in this graph, you can see the peak over mean ingress rate drastically dropping after several days of buffering in an upper tier, let's say a hard disk drive tier. So by staging, we can maximize the write drive utilization and minimize the system costs. So I threw a lot of things at you. If we kind of step back and we take a data-centric view of the entire system, data comes into the system, we stage it, we then do all the relevant erasure coding and error correction. I don't have time to go into a lot of detail about that, but please check out our paper. In particular, because we use a worm media, we're actually using network codes that have extremely large stripe set sizes, because we don't have to worry about in-place updates, so we don't use things like Reed-Solomon. We describe that more in the SOSP paper. We then write entire coding sets at a time, so we write the whole media, gets written all at once from the top, from the bottom of the media all the way up to the top. And then we do what's called a verify. So this is something that's kind of unique to the Silica system. So because we use different technologies to read and write, we read with polarization microscopy, we want to do one whole read of a platter from beginning to end after the platter's been written, just to guarantee that the data is readable with the same technology that's going to be used to read it for the rest of its lifetime. But it's important to mention, in contrast to magnetic media, we only have to do this once. So we only do this once after the data is written, and then the platter spends the rest of its life in the library, occasionally servicing on-demand reads from there. So now we come to the library. So in building the library and building the hardware that kind of brings the whole system together, We have a couple of design principles that came from the workload analysis. So, the write and the read bandwidth needs to be deployed in a modular fashion so we can provision and scale it independently, and we saw why that's important from the workload analysis. And it's also really, really important that however we design this, we minimize mechanical overheads in the system. And then we had two other principles that we think any sort of large-scale archival system should follow, which is that data at rest should never consume any resources, and the lifetime of the library should really match the lifetime of the data center building that it's deployed in, without any sort of need for mass media migration or sort of equipment migration. So a Silica library looks roughly like this. You have a write rack. A write rack can write multiple platters concurrently. You can think around the order of 8 to 10 platters. You have a read rack that can hold around 20 platters at a time, and it can read around 10 platters concurrently, and I'm going to talk a lot more about that later. And then you have storage racks that are completely passive, which you can scale depending on how much data a write rack is expected to write over the lifetime of a library until a library is full. And then we have another reader rack at the end for fault tolerance and availability, in case you get a partition in the middle and you get any sort of robots stuck on there. Well, that'll make a lot more sense in a second. It's important also to say that with this kind of modular design, you can scale write, read, and storage racks independently from each other, depending on what the needs are in the particular data center that you're operating in. So depending on what the characteristics of the workload are, you can scale these racks differently. So I'm going to show you a prototype of this library that we built in our lab in Cambridge. So this is a completely different it's a novel design that's inspired by warehouse robotics, so the kind of robots you have for Ocado is the big one in the UK. I'm not sure what the biggest one is here, but effectively robots that pick groceries. It's kind of inspired by that. So we have storage racks that are completely passive that you see there. They do not consume any sort of power to store the media. The media is just sitting on the shelves, doesn't consume, it's not encased in anything, which also reduces the emissions and environmental costs necessary in producing the media. And we have these little robots that primarily move horizontally across racks, moving glass platters around, but they also can crab. They can move between rails like we saw, which gives you all-to-all addressability between every platter and every reader in the system, which is great for fault tolerance. We talk about that more in the paper. It also means that, in the event that, let's say, a robot gets stuck, other robots can come in and service the platters that are on that shelf, so you can maintain availability by simply reconstructing from your erasure coding set. And unlike tape libraries, these robots have much smaller blast radius. So when a tape library robot fails, effectively your entire library, or however many frames that robot addresses, are unavailable. In this case, the blast radius of each of these robots is much smaller. The other thing I should mention, going back to the air gap property, we've actually designed this such that once a platter is written, these robots can only move platters out of a writer and into the library. It's physically impossible for a robot to take a platter and put it back into a writer. The writers only get fed from a completely different source of pristine glass that's not connected to the rail network. So even in the most unlikely case of malicious intent, it's not possible to hijack a robot, let's say, and then overwrite someone's data. So this goes further than tape libraries do today in terms of providing air gap property. And the other thing that shuttles do is, in contrast to tape robots, they parallelize the media fetching. So we can now have many media fetches happening in parallel. And this is just showing you what picking and placing looks like. So the shuttles come along, they can pick pieces of glass and then take them to the readers and then take them back from the readers and place them back in the shelves. So how do we evaluate this design? So to evaluate the performance of what a cloud service backed by these types of libraries would look like, we used a discrete event simulator, which was seeded with measurements from the real hardware prototype that we built in the lab, cross-validated in terms of mechanical motion, picking placing times, motion profiles, all of that, it's completely cross-validated. And to actually to evaluate and generate the load, we used traces from the system that we analyzed in the workload analysis. So in particular, what we did is we looked at 12-hour intervals across the 6 months of the workload we were looking at, and we picked 3 representative periods. Typical, which is just a typical 12-hour period. IOPS, which is the 12-hour period with the most number of read IOs, and volume, which is the 12-hour period with the most number of bytes read. So these are kind of a typical day, and then 2 kind of extremes for different types of extremes, IOPS and bandwidth. And we focused on these questions. How much does the read drive throughput affect system SLO? How efficient are our shuttles? Can we get good utilization of the read drives with our design? And what is the library going to behave like when it's full and it's at the end of its life? So there's more in the paper, or you can talk to me if you're curious. But this is what I'm going to focus on for the rest of the talk. So the first one is, how sensitive are we to the read drive throughput on the system SLO? So to do this, we simulated a data center-sized service backed by Silica libraries. Each library has 20 read drives, 20 shuttles, and the number of platters in the library was proportional to how much data there was in the tape-based archival system during trace time. And the metric that we focused on was tail latency, so 3 nines tail latency, and we were looking roughly at an archival service SLO on the order of 15 terabytes, which is quite similar to what most archival service offerings are today. And these are the results. So you can see the tail completion time in hours on the y-axis as a function of read drive throughput on the x-axis. And you might expect that at least the bandwidth intensive workload might need tape-like throughputs, but actually even at 30 megabytes a second, all of these workloads finish within SLO. And in particular, we get diminishing returns past 60 megabytes per second. So for a lot of the subsequent analysis, we actually picked 60 megabytes a second as kind of a representative number for read drive throughput. And so to achieve this, minimizing mechanical overhead is really crucial. And Silica has several advantages here. One is we use a media that is random access in contrast to spooling tapes. So again, once it's mounted, we don't need to wait to spool to the location that we want to read from. We just seek quickly and then do our I/O. The library design has the shuttles, which completely parallelize media fetches. And the last one is we don't need to wait for the media to spin up or stabilize before performing an I/O like a hard disk drive does, right? So all of these factors coming together have a significant impact. So how efficient are the shuttles? To answer that, we implemented another baseline in the simulation called no shuttles. It's not achievable in practice. So it's a platter is loaded as soon as a read drive is available, so it simulates in some sense infinitely fast shuttles, which obviously you couldn't do in practice, but it's useful because it gives you a lower bound of how well you could hope to get, given that you still have to do the actual read and service the I/O. And so these are the kind of 2 extremes. I'm not going to show typical because it's not as interesting, but these are the kind of 2 extremes. IOPS, where you have the most number of IOs, is where you expect to have the most number of platter swaps between different platters because you have lots of different IOs to serve. And here you see effectively the most amount of shuttle overhead. And on the right side, you have volume, where you're dominated by mostly drive operations, since you spend most of your time servicing the actual I/O. And here you see the overhead is less noticeable. So a typical workload sits somewhere between these two. So, with the current shuttles, we are able to get great performance. Perhaps with more sophisticated policies for scheduling, path planning, things like that, we can maybe close the gap and get even better. Now, the next thing I want to look at is read drive utilization. So you'll recall that the read workload is quite bursty. So regardless of how good of a job we do of load balancing, we have to provision the readers to be able to cope with bursts, right? It's just like in any system. But that means that during non-peak periods, there is spare read capacity in the system that goes unutilized. And so we've designed the read drive to have 2 slots and have a fast switching mechanism that can effectively pipeline 2 different read streams. So you have one read slot at the top, you're doing your read, and then in parallel, you can load the other platter. Then you can do a fast, what we call fast switching, where you're effectively switching the optical path from the first slot to the second slot. And you mount the platter, do your read of the second platter, and then unmount and quickly switch back optically to the first platter, and you keep reading. So effectively, it's just pipelining. You can think of it as a physical realization of double buffering in software. Now, if you'll remember, I also said that in Silica, we need to verify every platter once after it's written. And so what we wanted to do is to see, can we use this spare read capacity in the system that goes unused during non-peak periods to service the verify workload. And this is particularly interesting because the verify workload can be time shifted, right? The only cost you pay for time shifting the verify workload is you need to stage the data slightly longer in your hard disk drive tier. So, if you have a customer peak, you can just simply shift the verify workload slightly in time. And so we wanted to see, can we get good read drive utilization by pipelining our verifies with the foreground customer workload? And it turns out we can. So in this graph, you see the breakdown between customer reads and verification. So overall, we're able to get over 96% reader utilization across all of the workloads. And in the bar graph, you see the breakdown between the foreground customer reads and the verification read streams. And for volume and IOPS, obviously the readers spend more of their time servicing customer reads. For IOPS, servicing slightly more since you have more platter switching happening, so you need to do more mount operations. So with fast switching, we have an efficient mechanism to maximize the utilization of the read drives. Now, the last bit of evaluation is, what is the performance of a full library going to be? So at the end of its lifetime, what kind of SLOs are we going to be able to satisfy? So obviously, we don't have a crystal ball. We can't see what the workload is going to look like. So we came up with a synthetic workload. We assumed 100 megabyte files, which is roughly the median that we have from the workload analysis. We assume a 5% yearly deletion rate, 10% cooldown rate, and the read rate, which basically puts the read rate of the library from 0.3 reads per second, which is when the workload analysis that we did was done, to about 1.6 reads per second for a full library. And this is the results. So on the y-axis, you see, again, tail completion time as a function of the workload rate. So you can see the full library is around 1.6, and it's over there. So with every kind of drive from 30, 60, 120 megabytes, we're able to comfortably be within 15-hour SLO. With 60 megabytes drives, we're at 8 hours. Obviously, if you have more aggressive workloads, you can add more read racks or shuttles to the library to be able to cope in case some of these assumptions about the cooldown rate or the deletion rate are different, and you have to service a more aggressive workload. So yeah, that's it. Thank you very much. I want to take a moment to acknowledge the extremely multidisciplinary team that we have. I'm the one standing up here and giving the talk, but it took many years and many people to make this happen. In particular, across all of these different disciplines that you see here. The names of the people here are those that were authors on the paper that we had last year, but many other people contributed and actually increasingly are contributing inside the company, inside Silica. So I want to acknowledge all of them and say, none of this would be possible without all of their work and effort. So Silica is now strongly on path to product development. And next, we're actually starting to look at how do we leverage this great group of people with such a broad and diverse skill set and look beyond archival storage to what we can do in the hotter storage space. So yeah, thanks very much. That's my talk.
Are you taking questions? Thank you. So impressive work with regard to showing it's an archival media, could last a long time. So that's one of the issues with regard to preservation of data. But another one is technological obsolescence, i.e. that the encoding, the software, the hardware is changing over time. We may be using, and say you want to keep something for 200 years. Who knows what that technology is going to look like in 200 years? So it's kind of the bigger issue, I think. So I could see that maybe you could increase the retention time before you have to change media, maybe from, say, 7 years with tape to 14 years. But could you go beyond that? And if so, it's almost an economic issue as much as a technology issue, futurist economic issue as well as technology. And how do we deal with that? Maybe there's, you could create an annuity on stored data that keeps people employed who can keep on migrating, finding new ways of being able to access the data. People that do try to recover preserved data oftentimes keeps a lot of old equipment around and pieces of old equipment so they can keep doing that. So there's this like thermodynamics as well as social technological issues around keeping data for a long time and making it accessible. So I'm just curious, if it seems like that's a bigger challenge in terms of bringing data into the future.
It is, yeah. So I don't have a full-on crisp answer to that, but it is something that keeps coming up. It is something that we've considered. So, in fact, recently there was something in the news. We did a proof of concept of what a Voyager disk V2 would look like actually written in glass. So there's a few things I would have to say on that. One is, from all the usual storage things, right? Make the media self-describing, make the, put your index on the platter so that it's self-describing. Beyond that, you then get into, how do you even, this is digital data. How do you even read the digital data? What I would say on that is, the principles for how to measure these changes in polarization are not something that was discovered 10 years ago, right? People had microscopes for hundreds of years, and in the 1800s, people were already measuring the polarization of light. So, from a first principles point of view, it is possible to kind of bootstrap your way up, even in terms of building a read measurement instrument. I guess it's about leaving instructions that are detailed enough to do that, right? The Voyager V2 proof of concept does make some attempt at that. I can send you a link to it. Pardon me? The V1 was a record. The second one that we did was actually a platter the same size as this, with actually at one point, in addition to data, at one point the instructions for how to bootstrap yourself turn into pictorial instructions, right? So you can even pick up a platter. And so, there are solutions along that line, I think. It is an important problem that I think requires a lot of thought. I think it involves also considering, what your failure mode for humanity is. Is it do we still have computers? Do we still have automation, right? To what sense, is standardizing and widely replicating the format going to help? But yeah, it is something important that needs to be acknowledged. I agree.
Quick question on your workload analysis. You said the workload was heavily dominated by writes with very small amounts of reads. But that's pretty much a function of the fact that a tape library is incredibly difficult to read from. You ask for data, you get it back hours later.
Sure.
If you change the access characteristics of the tape library, do you think the workload would change and balance out for more reads? If it became a lot easier to read, people would read from it more?
Yeah, possibly. And I think, well, so yeah, two things. Yes, I think so. I think with better systems, more, if you think about the four verticals that I showed at the beginning, right? I think a lot more people would be using, long-term archive and even getting closer to active archive if the performance was better. The second thing is, I think if you look at, and we can talk about this offline, but I think if you look at the evaluation results, you can see that even with the design that we have, there is actually a lot of slack to service more aggressive workloads that have even higher read rates. And so, yeah, absolutely, the workload might change, and because people would actually start using archive more if you're able to offer better. So, yeah, that's what we hope with this. I think I'm over my time. So
yep, right at time. Perfect.
Thank you.
Thank you, Jan.